Hi everyone. So today we're going to be starting with vector spaces. But first, I just want to go through a quick little bit on another method of finding the inverse of a matrix. Okay, so some of you may have seen this before, but it's a nice method to find the inverse using row operations. Okay, instead of that adjugate matrix that we looked at last time. Okay, so finding the inverse using row operations. So let's say we have a matrix A. Okay, and this is given by 1, 2, minus 1, minus 2, 0, 1, and then 1, minus 1, 0. Okay, we want to find the inverse. Now, first you need to check that the determinant is non-zero, so you can check that for yourself, but let's just go straight to the method. Okay, so what we do is we construct an augmented matrix where the left-hand side is the matrix that's given. So 1, 2, minus 1, minus 2, 0, 1, 1, minus 1, 0. And then we do that vertical line like we used to separate the variables coefficients from the right-hand side of those equations. And then on the right-hand side, we put an identity matrix. So 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so left-hand side, we've got our matrix A. Right-hand side, we've got the identity matrix. Okay, so since this is a 3 by 3 matrix, we've got a 3 by 3 identity. Okay, but this works for any n by n matrix. Okay, so what we need to do is get this left-hand side to look like the identity matrix, and then the right-hand side will become the inverse. Okay, so we turn the left-hand side into the identity matrix using row operations. Then the right-hand side, okay, which was previously the identity matrix, will become the inverse. Okay, so if we do row operations to make the left-hand side look like the identity, then the right-hand side will become the inverse. Okay, so let's go ahead and do that. Okay, so let's just write out our augmented matrix again. So we've got 1, 2, minus 1, 1, 0, 0, minus 2, 0, 1, 0, 1, 0, and 1, minus 1, 0 with 0, 0, 1. Okay, so the first thing we need to do is to get this first element to be a 1. Okay, so it's already a 1, so that bit's done. Now the elements below, so those two there, we need those to be zeros. So the way we can do that is if we take row 2 and add 2 times row 1. So then the minus 2 and the 2 will cancel. So with row 3, we can do row 3 minus row 1. Okay, then the 1 and the 1 will cancel. Okay, so if we perform these two row operations, we'll get the following. 1, 2, minus 1, 1, 0, 0. So that stays the same. And then if we add 2 of row 1 onto row 2, we're going to get 0, 4, minus 1, 2, 1, 0. And if we take row 3 and subtract row 1, we're going to get 0, minus 3, 1, minus 1, 0, 1. Okay, so our first column is now done. Okay, what we need to do next is look at the second column and the second column, second row. So this 4, that needs to become a 1. So we could divide through by 4, but then we're going to be working with fractions. That's not the nicest. So instead, we can take row 2 and add row 3. That will turn the 4 into a 1. So let's do that. So we're going to get 1, 2, minus 1, 1, 0, 0, 0, 1, 0. And then we're adding row 3 there. So 2 minus 1, that's 1, 1, and 1. And then the last row, that stays the same. 0, minus 3, 1, minus 1, 0, 1. Okay, so now we've got that to be a 1, which is what we wanted. Now the other two elements, the one at the top and the one at the bottom, we need those to be zeros. So what we can do is take row 1 and minus 2 times row 2. Then the 2 minus the 2, that will give us a 0, which is what we want. And for the last row, we can take row 3 and we can add 3 times row 2. Okay, because then the minus 3 plus the 3, that will give us a 0, which is what we want. Okay, so let's perform those two operations. So if we do that, we're going to get 1, 0, minus 1 with minus 1, minus 2, minus 1, 0, 1, 0, 1, 1, 1. And then the last row, that's going to become 0, 0, 1 with 2, 3, 4. Okay, so now you see that the second column is done. Okay, so we move on to the third column. Okay, third column, third row, we need that to be a 1. It is a 1, so that's done. And then the next two elements in that column, they need to be zeros. So this minus 1, that needs to be a 0. And we see for the second row, we already have a 0, so we don't need to worry about that. Okay, so we need to get rid of that minus 1. So what we can do is take row 1 and add row 3. Okay, because then the minus 1 plus the 1, they're going to cancel to give us a 0, which is what we need. So let's do that. So we're going to have 1, 0, 0. Okay, and then adding that, we're going to get 1, 1, 3, 0, 1, 0, 0, 0, 1. And then everything else stays the same there. Okay. So now the left-hand side looks like the identity because we've got 1, 1, 1, and then zeros everywhere else. Okay, so that's the identity on the left-hand side, which means this right-hand side is our inverse matrix. So a inverse is going to be 1, 1, 3, 1, 1, 1, 2, 3, 4. Okay, so that is just another method of finding the inverse of a matrix. Now, in the assessments, I might say use this method or that method. Okay, in the question, then please use that method because that's what I'm testing. However, if I don't specify any method, then you're free to choose whichever method you want. Okay, so you only need to use a specific method if I mention it in the question. So if I don't say anything, you're free to choose. Okay, so that's it for the matrix stuff for now. We're going to be moving on to the new section on vector spaces and more specifically Rn as a vector space. Okay, so let's start that. Okay, so the idea of vector spaces is very general. However, for now, we are only going to consider a very special vector space that we call Rn. Okay, and this n, for now, is just going to take on the values of 2 and 3. Okay, so R2 and R3, just for simplicity. Okay, so before we get on to the idea of a vector space, let's just quickly recall the definition for the Cartesian product. So recall the Cartesian product of sets A and B is given by A cross B, and this is a new set of elements AB in brackets like that, such that the little a is from the set A and the little b is from the set B. Okay. And of course, we could do the Cartesian product of three sets. So we could have A cross B cross C, and this would be the three elements tuple A, B, C, such that little a is from A, little b is from B, and little c is from C. Okay, so that's the Cartesian product of three sets. And the result is another set. So what we're going to look at now is what happens if we take the Cartesian product of the real numbers with itself. So we will do the same thing, but with copies of R. Okay, so we're going to take the sets of real numbers and do the Cartesian product with itself. So we can look at R cross R, and as a set, this is equal to AB, such that A and B are both from the real numbers. Okay, because it's identical copies for both sets. Okay, and now just a little bit of notation. Since we've got two copies of R in this Cartesian product, so we can think of this as R2, like a R squared, because there's two of them. Yeah, but that's just notation. And then we can also look at R cross R cross R. So now we've got three of them. So this is going to be the three tuple A, B, C, such that A, B, and C are all real numbers. And since we've taken three copies of R, we can call this R3. And in general, we can do this with n copies. So let's say we have R cross, and then we have n many of them. So here we have n many copies. Okay, we have the same sort of thing. This is going to be the set. A1 up to an as an n tuple, where each of the AR, okay, each AR inside this tuple is a real number. And since we have taken n copies, this is going to be Rn. Okay, so that's the general set that we're going to be working with, Rn. Okay, that one over there. Okay, so far we have a set of elements. Here we have a set of elements. Okay, we call it Rn in general. But we will now add two operations to these to the set. So remember when we went over matrices, we had the set of matrices, so like 3x3 matrices or 2x3 matrices. We had a set where all of them had the same size. And on the set, we added two operations. First, we added the addition or subtraction between matrices. We did the scalar multiplication. And later on, we looked at the third operation of multiplication. Okay, so those were three operations that we added. Here, we are only going to add those first two. Okay, so we're going to add addition. We're going to add the operation of addition, which we will call vector addition, and we will add that scalar multiplication. We'll keep the name. Okay, so later on, we will look at products. Yeah, but for now, just the addition and scalar multiplication. Okay, so the first one, we call vector addition. Okay, vector because this is called a vector space. Okay, so we use that name. Okay, so how do we define this? So let's say we are working with R3, for example. So example in R3. If I have two vectors from R3, that's what we call them. Let's say V is going to be A, B, C. It's a 3 tuple with 3 real numbers, so A, B, C. So just a little bit of notation. Sometimes you can just write it as V. Sometimes there's a little line at the top. Sometimes you'll see there's a line at the bottom, or maybe you'll see a little arrow at the top. That's all just notation for the same thing. So these elements of R3, you can write these elements differently. So V with the line at the top, V with the line at the bottom, a little arrow at the top. Sometimes you'll just see V. Okay, so they all mean the same thing, means this element here. Okay, and if we have an element U, let's say it's X, Y, Z. Okay, so both of these are from R3. Okay, so that's just from the set of the 3 tuples. So what we want to do now is define addition between these two. So we got one, we got another. How do we add them together? So V plus U is going to be this A, B, C element plus the X, Y, Z element. So what we do is we add them component-wise, okay, or element-wise or point-wise. You might hear those phrases. So the first element with the first element, we add those. The second element with the second element, we add those. The third element with the third element, we add those. And we end up with another vector, another 3 tuple. It's going to be A plus X, B plus Y, C plus Z. Okay, so you see how we just added them component-wise. Okay, like that. Okay, so that's how we define addition for these vectors. If we had vectors from R2, we would just add the first components, the first component from the first one and the second, and then add the second components as well. Okay, and you can generalize this to Rn as well. Okay, you just do it component-wise like this. Okay, so that's vector addition. The next one, the next operation is called scalar multiplication. Okay, and it works very similar to what we did with matrices. So let's do an example in R3 again. Yeah, but it works for any Rn. So we're going to take a scalar, let's call it K. So that is just any real number. Okay, exactly the same as what we had with matrices. You can multiply a matrix by any real number. We can also multiply a vector by any real number. Okay, so we've got our scalar and we've got a vector, let's say X, Y, Z from R3. Okay, so what we want to do is define this operation of K times V. In other words, K times X, Y, Z. We do it very similar to what we do with matrices. The scalar K is going to multiply into each individual component. So the K is going to go inside each element here, and we're going to get Kx, Ky, and Kz. Yeah, and if you had Rn, you would do it for each of the n entries. Okay, so that is scalar multiplication. So we've got addition, and of course you can do the same thing with subtraction. Just replace the pluses with minuses, and scalar multiplication. Now with matrices, we had matrix multiplication. We will see later on, we're going to add 2 types of products. So you can think of it like a multiplication to this vector space. Okay, but we're going to do that later on. Okay, before we get to that, we need to look at vector representations. So far we've just seen these vectors as n tuples of real numbers. But if you did physics in high school, if you're doing physics in first year, you might know that there's another way of representing vectors using arrows. Okay, so let's look at the arrow representation. Sorry, arrow representation. So something like that. Okay, so let's work in R2. So in R2, the vectors look like v equals x comma y. Okay, so it's a two tuple, two elements that are real numbers. So the way we draw this arrow is we imagine the Cartesian plane. We've got the x and the y. We start off at the origin. That's the base of the arrow. And we look at the vector as a point. So example, v equals 1, 2. The x part is 1, so we move across 1. And the y part is 2, so we move up 2. And that gives us this point here, 1, 2. Now, that's not the vector, that's the point 1, 2. The vector is going to be the arrow from the origin to that point. So it's something like that. Okay, so that is the vector 1, 2. And we can draw another vector, let's say here. Okay, so this blue vector, this is going to be, let's say, w, and that's going to be 2, 0. Okay, because it's 2 along the x direction and 0 along the y direction. So that's 2, 0. Okay, and then you can sketch other vectors as well. Okay, so that is the arrow representation of vectors. Now, we could also use this arrow representation to work out the addition of vectors. So let's say we've got v and w, and we want to do v plus w. Now, on the side, we could work that out because we know how to do vector addition. So v plus w would be 1, 2 for v, plus 2, 0 for w, and that's going to be 3, 2. That's going to be the sum of the vectors. Now, if you want to do it visually using this arrow representation, what we do is we take these two vectors and we imagine a parallelogram where these two vectors are the sides. So if w is along the bottom, we're going to copy w at the top, and v is along one of the sides, we copy v on the side here, okay, to complete the parallelogram. Okay, because remember, the opposite sides are equal and parallel. Now, the third vector, which is the sum of these two, is going to be the diagonal here. Okay, so this diagonal of the parallelogram produced by the two, that's going to be v plus w. Okay, so that's with the addition. With the scalar multiplication, we just need to imagine these vectors, but then being stretched by an amount. So if this is w, and we're interested in 2 times w, we imagine this vector, but double the length. Okay, so double the length of this vector might be somewhere here. Okay, so that will be 2w. Okay, it's twice as long. Okay, now, while we're on this topic of the length of a vector, let's define it properly in terms of its components. So the length, okay, now there's a couple of ways of mentioning this. So we can say the length of a vector, or we can say the norm of a vector, or the magnitude. Okay, so the length or norm or magnitude, it all means the same thing, of a vector is given by the length of that arrow that we made. Okay, so if we have a vector and we draw it as an arrow, the length of an arrow we say is the length of the vector. Okay, so since we're drawing all of them from the origin, if we want to know the length, we just need to use the distance formula from the origin to the end of the arrow. That's where the point is. So if we look at this example with V, the length of V, or the norm of V, or the magnitude of V, we write as a vertical line, V vertical line. So it's like the absolute value. Okay, but it's not the absolute value of a number, it's a vector inside there. This is equal to its length, but we can just use the distance formula. So this is going to be 1 squared plus 2 squared, okay, for the x part and the y part. So that's going to be √5. Okay, so that's the length of this vector. Now, in general, we take the sum of the squares of the components and then take the square root. So if we had a vector W, which was x, y, z, then the length of W would be the square root, and then we just use the distance formula again. So it would be x squared plus y squared plus z squared. Okay, so that gives us the length of the vector. And if there were more components, then you would just increase that sum. So if this was vectors in R4, it would be x squared plus y squared plus z squared, and then maybe plus w squared, for example. Okay, so that's the length or norm or magnitude. Okay, so you might see any of these three terms mentioned. Okay, so now we know how to find the length of a vector. That gives us a special class of vectors called unit vectors. Okay, so there is a special class of vectors called unit vectors. Which have length of 1. Okay, so if you calculate the length of a vector and you get an answer of 1, then we call that vector a unit vector. Okay, so just a little bit of notation. So vectors are written as, like we said, V with the bar at the top, V with the line underneath, V with the little arrow on top. So those are all different ways of writing the vector. There's a special way of writing unit vectors. So unit vectors are written as V with a little hat. Okay, so we can read that as V hat, and this means that it has a length of 1. So the length of V hat is always 1. Okay, so that's how we can quickly identify if a vector has length 1 or not. Okay, you put the little hat on, and that means it has length 1. Okay, and then last thing for today, there are 3 special unit vectors that point in the X, Y, and Z directions, respectively. Okay, so the unit vector that points in the X direction, we call that X hat. And this is given by 1, 0, 0 in R3. In R2, it would just be 1, 0. Okay, sometimes we call it I hat, and that's the same thing, 1, 0, 0. Okay, so that is for the X direction. Okay, so going along the X-axis, that's the unit vector in that particular direction. For the Y direction, we have Y hat. Okay, that's 0, 1, 0 if you're working in R3, or just 0, 1 if you're working in R2. Or we sometimes call it J hat. That's 0, 1, 0, and that's for the Y direction. And then I'm sure you can guess this for the Z direction. We have Z hat. That's going to be 0, 0, 1. Okay, in R3. Because you've got X, Y, Z for 3 dimensions, or we call it K hat, and that is 0, 0, 1. And this is for the Z direction. Okay, so these are the 3 special unit vectors that we have special names for. So when you're writing down vectors, you can use A, B, C, all the way to Z, that's fine. However, these over here, these labels X, Y, Z, R, J, K, those are specifically for these unit vectors. So you can't use these labels for other vectors. Okay, it's only for these 3 here. Okay, so that's enough for today. So next time we will go through more examples on vectors, looking at their operations, more on sketching them. And then we will introduce the other 2 operations between vectors, and that is the dot product. So very similar to the dot product we used with matrices, and the cross product. Okay, so 2 products that we need to introduce. Okay. As always, if you have any questions, please feel free to email me, or you can post a message on the WhatsApp group. Okay, so our class tutors are also available on the WhatsApp group, so they can also help with any questions that you have. Okay, but I will see you in the next lecture. Bye, everyone.